Hello dear students, so we are back with mathematics sessions, and the first chapter what we are going to take is relations and functions. And relations functions you have to be very careful, as the relations part, sets and relations, is basically a part of your board exams as well as your JEE mains, but interestingly it is not a part of your advanced. Whereas functions, I consider it to be the most important topic in mathematics, is a part of your board exams, mains as well as advanced. So let us start with the chapter relations and functions. So I'll put your mathematics and our topic name is, first we are going to start with relations. Again we are breaking this topic into two units. One will be relations and then functions. So let us start with relations. So to start with, we know what is a set. For example, is a collection of meaningful or defined elements. For example, this is a set A. Similarly, I can create one more set B. Let us say that is set of two elements x and y. Both are finite sets, you can see. Both are non-empty set. Finite set means if the number of elements can be countable. Infinite sets, for example, a set of natural numbers is an infinite set. Both are non-void. Non-void or non-empty meaning is same. So basically, if you see here carefully, suppose I create this Cartesian product of A and B. Cartesian product of set A and B. So that will be denoted like this, A cross B. Here cross means Cartesian product. It is not some usual multiplication. Cross, A cross B, Cartesian product of A and B. So that will be, means you need to form the ordered pairs of A and B. So there will be 1x, 1y, 2x, 2y, 3x, 3y. 1x, 1y, 2x, 2y, 3x, 3y. That is your Cartesian product. This is the meaning of Cartesian product. If you see carefully, then your elements of set A, how many elements were there? 3 elements were there. And how many elements were there in set B? 2 elements. This is known as cardinal number. Cardinal number of a set. Cardinal number of a set. Cardinal number of a set means number of elements of that set. Cardinal number of set. So n of A is 3, n of B is 2. And if I ask you what is n of A cross B, that is Cartesian product of A and B. So that will be 1, 2, 3, 4, 5, 6. 6. Which you can simply do 3 into 2. 3 into 2 is 6. Now here, what is important to understand is that what is important here to understand is that relation is nothing but a subset of, relation is a subset of your Cartesian product of A and B. A relation is nothing but a subset of your Cartesian product of A and B. So this is your Cartesian product of A and B. So how many subsets you can create? So number of subsets. Number of subsets. For example, suppose there is a set A. Set A is there, which is what? 1, 2, 3. Then how many subsets you can create of this set? 5. Your void set is a subset of every set. 1, 2, 3, 1, 2, 1, 3, 2, 3 and 1, 2, 3. Observe here, these many subsets are there. 5, 1, 2, 3, 1, 2, 1, 3, 2, 3 and 1, 2, 3. If you count 1, 2, 3, 4, 5, 6, 7, 8. And number of subsets of A. Number of subsets of A are 8. It means this is nothing but 2 to the power 3. 3 elements are there. So I am writing 2 to the power 3. Similarly, suppose you in your set B, how many elements are there? X and Y. If you want to calculate the number of subsets. So here number of subsets will be what? 5. Because 5 is a subset of every set and the set is a subset of itself. 5, X, Y and XY. So 1, 2, 3, 4, which is basically 2 square. 2 square. So your cardinal number, it means that it is nothing but number of subsets of set A. Number of subsets of any set A is 2 to the power n, its cardinal number. Now in A cross B, your Cartesian product, how many elements are there? 1, 2, 3, 4, 5, 6, which is your A cross B. So what I am saying is that number of subsets or number of relations, because relation is nothing but what? Subset. Relation is a subset of A cross B. But the question is how many subsets are there? It means that many number of relations will be there, because relation is a subset. Now in a set A, if there is a set A, and if it has m elements, there is a set B, it has n elements, then set A cross B, because this is also a set only. If you see carefully, it is also a set only, and its elements are nothing but the ordered pairs. Here for set A there are singular elements, for set B also singular elements are there, but for the Cartesian product the sets are, your elements are nothing but your ordered pairs. This is your ordered pair. So in A cross B or Cartesian product of A and B, the number of elements will be m into n. So number of subsets will be what? Number of subsets of A cross B will be nothing but 2 power m into n, because for this number of subsets are how many? 2 power m. For this number of subsets are 2 power n. So for this number of subsets will be 2 power mn. It means that as a subset is nothing but a relation, it means that number of relations are nothing but 2 power m into n, 2 power m into n. This is your JEE Mains question. I hope this concept is clear to you. So if there is a set A, set B, you can easily create your Cartesian product. Similarly, you can create A cross A also. A cross A. A cross A will be what? 1 1 1 2 1 3 2 1 2 2 2 3 3 1 3 2 3 3. Similarly, you can create B cross B, XX XY YX YY. So there are ways to create this. You have to basically create the ordered pairs. So I hope this concept is clear. Now suppose this is our Cartesian product A cross B. Suppose I am writing R1, means the first relation. I am saying that 1y 3x, this is a relation from A to B. R1 is a relation from A to B. So I have to check whether it is a relation or not. Yes, 1y and 3x, both of them are belonging to this set. It means this is a subset of this. It means this is a relation. Suppose R2 is given, R3 is given, R4 is given. R2 is given as 2x and 3y. This is also a relation. Suppose R3 is given 2x, 3y, 3z. Then this will not be a relation, because z does not belong to that. So relation is nothing but relation is a subset of your Cartesian product. So you have to check whether your ordered pairs are belonging to that Cartesian product or not. R4, suppose someone says R4 is 5, then yes, that is a relation from A to B, because phi is a subset of every set and a set is a subset of itself, and apart from that you can calculate how many more subsets are there. So a relation is nothing but a subset. So now we are clear that there is a set A, there is a set B. From set A to B we can create the Cartesian product, and its subsets will nothing but become relations, which you can write as R1, R2, R3, and based on the number of relations. So that is your concept of relation. Now let us discuss some important terms regarded to a relation. I hope this concept is clear to you. You can note it down. Let us continue with some important terms regarding to a set. So first is domain of a relation. Domain of a relation. Domain of a relation. Let us try to understand what is the meaning of domain of a relation. For example, there is a set A. I will use the same set 1 2 3. Set B is XY. So I can create Cartesian product of A and B, which is 1x 1y 2x 2y 3x 3y. Now I am writing relation R1. R1 is 1x 1y. R2 is 1x 2x 2y, and R3 is 1x 2x 1y 2y 3x and 3y. Now Try to understand the meaning of domain. Domain of a relation, domain denoted as capital D. Domain of a relation is nothing but the collection of first elements of the ordered pairs of that relation. The collection of domain means the collection of, it is a set, domain is a set only, but which set? It comprises of the collection of the first elements of the ordered pair. You see, this is the ordered pair. So the collection of first element of the ordered pair, here first elements are what? 1 x, it means 1, and 1 y means 1. Yani your domain is nothing but a set comprising of 1. This is your domain. For this, D will be 1, 2, because 2 is again repeated. In a set, an element should not get repeated. So my answer is 1, 2. For this, the domain will be what? 1, 2, 3. 1, 2 and 3. Elements should always be separated by comma, and no element should repeat in a set. In a set, element should never be repeated, whether it's a singular element or the ordered pair. Ordered pair should also not be repeated. Means basically an element should not get repeated in a set. So this is your domain. Domain means the collection of first element of ordered pair. Collection of first element of ordered pair. Similarly, you can define range of a relation. Range of a relation. See, this is your Cartesian product. This is as it is, but relations may be different because relations are what? It's subsets. So you can create as many 2 power mn subsets. Here your mn is 6, 3 plus 3. So 2 power 6, you are understanding. So many subsets can be created. So domain of that particular relation. Okay, domain of that particular relation. So similarly, range of a relation is nothing but collection of second element of the ordered pair. Range means collection of second element of the ordered pair. Domain and range. For example, here now range to be denoted as capital R. So we have to be careful. Relation also we use the your symbol capital R, and range also we use the symbol capital R. But you will get to know the meaning when what is used. So capital R. So here your x and y. This is your x and y. What about here? Here also x and y. Here also range is x comma y. What about this question? X, y, x and y only. X and y. So that is as far as your domain and range of a relation is concerned. I hope this makes sense to you. Now let us do one thing. Let us see types of relations one by one. Types of relations. Types of relations. Types of relations. So for example, the first type is basically your void relation. Void relation, or you can also call it as empty relation. Empty relation. Empty relation. So empty relation, what it is defined? Empty relation R is nothing but phi. Empty relation R is nothing but phi. See, to the phi you should not put another brackets, because phi itself means this. This is a set containing nothing. Phi means a set containing nothing. So separately don't put any brackets to phi. You are understanding? The meaning of phi is this. So your relation is a void relation. It means it contains nothing. For example, let us try to have an example. Let us say your set is A is there 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And you are creating relations on set A to A. Relations on set A to A. A to A means A is this, and the another set B. B is also A only. So basically you will get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, then 2, 1, 2, 2. Similarly, you will get all the relations or your Cartesian product. Now relation R is defined such that relation R is a collection of your ordered pairs A, B, such that A plus B is equals to 20. Relation R, now you see how we are defining the relation R. Set A is there. This your Cartesian product is defined on A to A. We can create B also, but what I am saying is B is nothing but A. So we are creating the Cartesian product of A and A only, which is A cross A. On that we are defining a relation. A specific relation R is there, such that R is a collection of ordered pair AB such that A plus B belongs to 20. Now, if you form the subsets, so 1 1 1 2 1 3 1 4 1 5 2 1 2 2 2 5 3 1 3 5 like that till 5 1 5 5. Maximum sum can be 10. No sum, I mean there is no ordered pair whose sum attained will be 20. So I can say that this is nothing but phi, or basically that is your void relation. I hope the meaning of void relation is clear to you. That is nothing but your phi. So that is your type 1 of relation, and void relation, also known as empty relation, or you can also call it as null relation, null set. So that is as far as the domain and range of a relation. This is your void relation. Now let me do one thing. Let me move to the second type of relation. Meanwhile you note it down. Okay, let us continue the types of relations. So our second relation, first relation already we have seen is void relation. Second relation is universal relation. Universal relation. Let us say there is a set 1 2 3. This is set A. Now always I will take set B as set A only, otherwise I will mention it there. If I have to take any other set B, I will mention it, otherwise your set B is same as set A. So we are defining your Cartesian product as A cross A. That is your Cartesian product. Now let us try to understand the meaning of universal relation. See, A cross A, which is your Cartesian product, that is also a relation, because A cross A is nothing but a set, and I told you a set is a subset of that set. A set is a subset of itself. A set is a subset of itself. So if you try to see the subsets of your Cartesian product A cross A, then what you are going to get? Phi, then you will get subsets, and the final set will be nothing but the Cartesian product. That product or that set is nothing but your universal relation. So your universal relation is nothing but your Cartesian product A into A. For example, let us say this is your A is 1 2 3. I am defining a set R. Let us define the set R such that it is a collection of ordered pairs AB such that mod of A minus B is greater than equals to 0. Mod of A minus B is greater than equals to 0. Yani your A, small a has to come from set A, small b has to come from set B, which is now set A, such that the difference of the elements should be greater than 0. So you know that modulus is always a greater than 0. So in this, if you try to collect, you will get what? 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. If you see carefully, 1 1 difference is what? 0, obviously equal to 0. 1 2 difference is minus 1. I mean A minus B minus 1, but minus 1 modulus is what? 1. Modulus of minus 1 is 1, modulus of minus 2 is 2, which is greater than 0. So you will always get all this, and this is nothing but what? Your A cross A. So this set is nothing but known as your universal relation. Universal relation. Universal relation. So domain of a universal relation is nothing but your set A, and range of a universal relation is set B, which in this case is set A only. So I hope that makes clarity about your universal relation. Third is your identity relation. Identity relation. Identity relation denoted like this, IA. I mean that is your R, but we are denoting it as IA. Even this universal relation you can denote it as U, capital U, universal relation. So identity relation, IA. So suppose again your set A is this 1 2 3, and we are defining your relations on Cartesian product A to A, A cross A. So your IA is nothing but A comma A, A comma A. Yani the element of set A and the element of set B, both should be same. A to A. It's a collection of, what is the meaning? How to read it? How to read it? R is a set of ordered pairs A, B such that mod of A minus B is greater than or equals to 0. So how to read it? Identity relation is a collection of A to A to A, such that A belongs to A and A, that another A belongs to B, which in this case is nothing but A. So here if you see your identity relation, that will be nothing but 1 1 2 2 3 3, 1 1 2 2 3 3. That is what I am saying is every element is related to itself. Every element is related to itself only. Every element is related to itself only. This is related to itself only. Suppose someone says, let us say R1 is 1 1 2 2. Is this identity relation? No, this is not an identity relation, because 3 belongs to A, but 3 is not related to A. 3 is not related to 3. 1 1 is there, 2 2 is there, but 3 belongs to A. 3 belongs to A, but where is 3 3? So this is not an identity relation. Let us say one more relation, 1 1 2 2 3 3 and 1 2. 1 1 is there, 2 2 is there, 3 3 is there, but 1 2, why it is there? 1 2 should not be there. So this is also not a identity relation, because every element should be related to itself only. It should not be related to any other element. Every element should be related to itself only. That is the meaning of identity relation. So I hope the meaning of, see, if you see carefully, then this will be one of the relations. See, this is a relation. This is a relation, but it is not an identity relation. Similarly, this is also a relation, but it is not an identity relation. We are talking about a specific relation. Same here. This is a relation, but this is which relation? This is universal relation. Void relation means phi, A to A, your last subset, which is your final A cross A. That is your universal. In between, so many relations are there. In that, we are finding which is identity. So identity is every element is related to itself only. I hope this makes clarity to you. And you can, okay, so we have seen 3 types of relations: void relation, phi, universal relation, A to A, which is your Cartesian product only. And we have also seen identity relation, every element should be related to itself only. Now the most important of all of them, relations 4 5 6, reflexive relation. Let us try to understand reflexive relation. Reflexive. So reflexive relation is that a relation R is said to be reflexive. Relation R is said to be reflexive if and only if AA belongs to R for every A belonging to A. See how I am defining. A relation R is said to be reflexive if and only if AA belongs to R. AA belongs to R for every A belonging to A. Example, let us say your A is 1 2 3 4. This is your A. We are defining a relation. Let us say R1. 1 1 2 2 3 3 4 4 1 2. Now for every A belonging to A, does 1 belongs to A? Yes. It means 1 1 should belong to R. Yes, it belongs. Does 2 belongs to A? Yes, it means 2 2 should belongs to R. Does 3 belongs to A? So 3 3 should belongs to R. Does 4 belongs to A? Yes. So 4 4 should belongs to R. This may be there. What I am saying is, if 1 is there, then 1 1 should be there. Apart from that, anything else may also be there. 1 may be related to something else also, may not be related also. For example, R2 1 1 2 2 3 3 4 4. This is also reflexive, this is also reflexive, because if 1 belongs to A, then 1 1 should belongs to A. See, try to understand. AA should belong to R. It is not that only AA should belong to R. AA should belong to R. Yani, what I am trying to say is that An element is related to itself. An element is related to itself. I am not saying that an element is related to itself only, that is for identity. This relation is reflexive as well as identity. This is only reflexive but not identity, because 1 2 is belonging to R. So it is not identity but it is reflective, because 1 1 2 2 3 3 4 4 all are there. Suppose R3 is there, R3 1 1 2 2 3 3 and 1 2. Is it reflexive? No, because where is 4 4? Because 4 belongs to A but 4 4 is not there. For every A belonging to A, we need to have that A to A. So that is the meaning of a reflexive relation. For example, suppose I am asking a question, a set of, suppose the set A is a set of natural numbers. Set A is set of natural numbers, and you are defining a relation on A to A. A to A. Okay. So I am asking, is this relation, is A to A, is relation A to A reflexive relation? Is relation A to A reflexive relation? This is my question. So if you see carefully, your set A is a set of natural numbers, yani 1 2 3 4 till infinite it will go. Now we are defining A to A. It means that 1 1 will be there, 1 2 1 3 and 1 2 till infinite. Similarly, then 2 1 2 2 will also be there. Then 3 1 3 2 3 3 will also be there. Like that, if you see carefully, then yes, it is a reflexive relation. If someone asks, is it identity? No, it is not identity, because 1 2 is also there. Identity means an element is related to itself only. Reflexive means an element is related to itself. So that is the meaning of your reflexive relation. So I hope it is clear to you. Now let us see relation number 5, which is your symmetric relation. Symmetric relation. More examples we will take, more depth questions we will take, but first let us try to understand the introduction part. Symmetric relation. Okay, symmetric relation. So symmetric relation means, let us say your set A is there, 1 2 set A is 1 2 3 4. Okay, so symmetric relation is nothing but a set R is said to be symmetric if and only if AB belongs to R, which implies BA belongs to R. If AB belongs to R, then BA should belong to R. If and only if means if this is there, then that should be there. For example, this is your set A. I am defining a relation R1. 1 2 2 1 1 3 3 1. Observe here. 1 2 is there. It means 2 1 should also be there. Yes, it is there. 1 3 is there. It means 3 1 should also be there. Yes, it is there. It means this is a symmetric relation. Let us take one more example. 1 1 1 2 2 1 1 1 1 1 is there. It means 1 1 should be there. Yes, it is there, because ordered pair should not be repeated. 1 2 is there. 2 1 is also there. Yes, it is there. Let us take one more example. R3 1 2 2 1 1 3. Here if you see 1 2 is there, very good. 2 1 is also there. 1 3 is there, but where is 3 1? If 1 3 is there, then 3 1 should also be there. So this is not symmetric. So I hope the meaning of symmetric is clear to you. If 1 2 is there, then 2 1 should also be there. If AB is there, then BA should also be there. Let us take one example. Let us say L is a set of all the lines. Set of all lines in a plane. L is a set of all lines in a plane. And we are defining a relation from L to L. R is a relation from L to L. Cartesian product L to L, such that R is a collection of L1, L2. R is a collection of L1, L2. Yani two lines. R is a collection of two lines L1, L2 such that let me write like this, defined as R is a relation from L to L, defined as R is a collection of L1, L2 such that L1 is perpendicular to L2. This is your question. L1 is perpendicular to L2. Now my question is it a symmetric relation? L1 is perpendicular to L2. Suppose this is your L1, this is your L2. So if L1 is perpendicular to L2, then L2 will also be perpendicular to L1. It means that if line 1 is perpendicular to line 2, then line 2 is also perpendicular to line 1. It means that what? It means that yes, it is a symmetric relation, because suppose 1 is perpendicular to 2, then 2 will be also perpendicular to 1. So both will be there in your set. If 1 is perpendicular to 3, then 3 will also be perpendicular to 1. So if a line is perpendicular to other line, then the other line is also perpendicular to this line. So like that you will get all AB and BA in your set. So yes, that is a symmetric relation, but it is not a reflexive relation, because a line is not perpendicular to itself. Here what you have to find? An element is related to itself only. A line cannot be perpendicular to itself. A line cannot be perpendicular to itself. So it is not, this is not reflexive, but it is symmetric. So I hope the meaning is clear to you. So note it down, and then I will move to the third type, which is transitive relation. Okay, so let us continue now with the another type, which is your transitive type. Transitive relation. So we have covered word relation, then we have gone to universal, identity, reflexive and symmetric. So 5 relations are over. This is number 6th, transitive relation. Let us try to understand. So relation is said to be transitive if and only if AB belongs to R and BC belongs to R. AB belongs to R, yani relation is said to be transitive if and only if your ordered pair AB belongs to relation R, BC belongs to relation R, then which implies that AC also should belongs to relation R. If AB belongs to R, BC belongs to R, then AC should also belongs to R. That is the meaning of your transitive relation. For example, let us say your set A is there 1, 2, 3, 4, 5. This is your set A. We are having Cartesian product A to A. In that we are defining some relations. Let us say R1 is there 1, 2, 2, 3, 1, 3, 1, 4. Let us say this is there. Now let us check it carefully. 1, 2 is there, 2, 3 is there. You have to see this, the second element and the first element. This correspondence has to be there. AB belongs to R, BC belongs to R, then AC should belongs to R. So 1, 2 is there, 2, 3 is there, then 1, 3 should be there. Yes, it is there. 1, 3 is there. Okay. What about this 1, 4? But there is no element starting with 4. So it means this relation, this condition does not hold. This condition is holding here. 1, 2 is there, 2, 3 is there, 1, 3 is there. So it is a transitive relation. You have to see this. If AB is there, BC is there, then AC should be there. If it is not there, not a problem. Let us see one more relation. 1, 1, 1, 2, 1, 3, 2, 4. Let us see this relation. 1, 1 is there, 1, 3 is there. So 1, 3 should be there. It is there. 1, 2 is there, 2, 4 is there. But where is 1, 4? 1, 4 is not there. So this is not transitive. So I hope it is clear to you. If AB is there, BC is there, then AC should be there. If it is not there, not a problem. Then it is transitive. I am saying if it is there and this is not there, then it will not be a transitive. Let us take few more examples. Let us say we are having a set L is there, which is a set of all the lines in a plane. All the lines in a plane. And we are defining relation R such that L1, L2. Relation R is a collection of two lines L1 and L2 such that L1 is parallel to L2. L1 is, let us say this is R1 and R2. L1, L2 such that L1 is perpendicular to L2. Now let us try to check whether this is, we will check it, symmetric, reflexive, transitive. Here also symmetric, reflexive, transitive. Let us check one by one. L1 is parallel to L2. A line is parallel to itself. Everyone knows two lines, coincident lines, we can also call them parallel lines. So it will be, let me make the order like this: reflexive, symmetric, transitive. So reflexive means if element A is there, then AA should be there. So your relation is L1 parallel to L2. It means every line is parallel to itself. So it is going to be reflexive. What about symmetric? Symmetric. If L1 is parallel to L2, then L2 is also parallel to L1. So it is symmetric also. What about transitive? If L1 is parallel to L2 and L2 is parallel to L3, then L1 is also parallel to L3. Once again, if L1 is parallel to L2 and L2 is parallel to L3, then L1 is also parallel to L3. So it is also transitive. Let us see the second relation R2. L1 is perpendicular to L2. Is it reflexive? Is a line perpendicular to itself? No, a line is not perpendicular to itself. A line is parallel to itself. You can say it is parallel to itself or coincident, but it is not perpendicular to itself. Is it symmetric? L1 perpendicular to L2. Symmetric means if AB belongs to R, then BA should also belongs to R. So if L1 is perpendicular to L2, then L2 is also perpendicular to L1. So it is symmetric. What about transitivity? Is it a transitive relation? If L1 is perpendicular to L2 and L2 is perpendicular to L3, then L1 and L3 are also perpendicular? No, they will become parallel. See here, this is your L1. L1 is perpendicular to L2. This is your L2. L1 is perpendicular to L2 and L2 is perpendicular to L3. L1 is perpendicular to L2, L2 perpendicular to L3, but L1 and L3 are not perpendicular, but they are parallel. So it will not be transitive. So I hope this makes sense about reflexive, symmetric and transitive relations. Now let us see the next type of relation, relation number 7, which is your equivalence relation. Equivalence relation. Equivalence relation. So equivalence relation R is said to be equivalence. A relation R is said to be equivalence if it is reflexive, symmetric, as well as transitive. If a relation is all of them, reflexive, symmetric as well as transitive, then we say that relation is equivalence relation. For example, you see this is reflexive, symmetric as well as transitive. So this relation would become a equivalence relation. So that is as far as the types of relations are concerned. 7 important types. Void relation, which is your phi, contains null element. Universal relation, which is basically your Cartesian product itself, A to A or A to B. Then we had your identity relation, every element should be related to itself only. Then we are having reflexive, an element is related to itself, other things may also be there, but if A is there, then AA should be there. Symmetric, if AB is there, then BA should be there. Transitive, if AB and BC both are there, if AB and BC both are there, then AC should be there. So that is as far as your transitive. And equivalence means if the relation corresponds to all the three, then we call it as a equivalence relation. Next is your inverse of a relation. Last concept, inverse of a relation. Inverse of a relation denoted as R inverse, like this, inverse of a relation. For example, from set A to B there is a relation R. Let us say it is 1 2 1 3 2 3. This is your relation R. What is its domain? 1, 2. Its domain is 1, 2. What is the meaning of domain of a relation? The collection of first elements of the ordered pairs. What is its range? Range is 2, 3. So its inverse would be nothing but you interchange A to B, interchange A and B. So that will be your 2, 1, 3, 1, 3, 2. This is your R inverse. Inverse of this relation is 2, 1, 3, 1, 3, 2. Means R inverse is nothing but if R is a collection of AB, if R is a collection of AB, then R inverse is a collection of your BA. So the domain of R inverse will be what? 2, 3. Domain will be 2, 3. The domain and the range of relation and its inverse would be interchanged. And what is the range? Range is 1, 2. You see here, this is your range of R inverse, which is same as the domain of R, and this is your domain of R inverse, which is same as your range of R. So that is your inverse relation. So these are the types of relations. I hope all the meanings are clear to you. Note it down and we are ready with problem sessions. So note it down. I am going to take a good number of problems. Note it down. Okay, so let us see this question. Basically there are 4 questions. What we have to tell them? Whether the relations are reflexive, symmetric or transitive. One by one we have to check. So first question, there are 3 parts. Let us see. There is a set A, B, C. 3 elements are there, A, B, C. Cardinal number is 3. Relations defined on set A. It means set B is also set A only. A to A. Cartesian product of A and A. So these are the relations. R1 is AA, AB, AC, BB, BC, CA, CB, CC. We need to check whether they are reflexive, symmetric or transitive. So let us start with the reflexive. Reflexive means AA, BB, CC should be there. Apart from that, anything else may also be there. But since A belongs to A, AA should be there, B belongs to B, BB should be there, and C belongs to C. C belongs to A. So CC should also be there. If you see here, AA is there, BB is there, CC is there. So it is reflexive. I am writing here, it is reflexive. What about symmetric? If AB is there, then BA should also be there. AB is there. Where is BA? AB is there. BA. BA is not there. So it is not symmetric. AB is there, but BA is not there. So it is not symmetric. Let us check transitive relation. So transitive means if AB is there and BC is there, then AC should also be there. So let us check here. AB, BC. AB is there, BC. So AC. Where is AC? AC is not there. See here. AB is there, BC is there, but AC is not there. Even if one pair is not there, then the whole transitivity will be lost. AB is there, BC is there, but AC, sorry, AC is there. AC is there. AB is there, BC is there, AC should be there. AC is there. Then, okay, AB is there, BC is there, AC is there. BB, BC, BC, CA, BA is not there. You see here BC is there, CA is there, but BA is not there. BC is there, CA is there, but BA is not there. So it is not transitive. I hope you got the first relationship. Let us see R2. So is it reflexive? No, because where is AA, BB, CC? So it is not reflexive. What about symmetric? AB is there, BA is there. Very good. AC is there, CA is there. So it is symmetric. Then transitive. AB, BC, AC. AB is there, BA is there. AB is there, BA is there. But where is AA? AA is not there. AB is there, BA is there. AA is not there. So it is not transitive. Let us see this. AB is there, BC is there, AC is not there. So it is not reflexive because AA, BB, CC is nothing is there. AB is there, but where is BS? It is not symmetric also. And transitive, AB is there, BC is there, but where is AC? CA is there, AC is not there, so it is not transitive. This is none. Basically it is none. Now let us see question number 2. I hope question 1 is clear to you. Fairly simple problem. Let us see question 2. Relation R is defined on set A. So relation R defined on set A means A to A. The question is R is 1 1 2 2 3 3 1 2 2 3. They are asking your reflexive, symmetric or transitive. So let us start. Reflexive 1 1 2 2 3 3 all are there, so it is reflexive. Symmetric 1 2 is there, but where is 2 1? So it is not symmetric. Transitive 1 2 is there, 2 3 is there, so where is 1 3? 1 3 is not there, so it is not transitive also. I hope question is clear. Let us see question number 3. A is related to B. Questions may be given like this also. Mainly in your mains they appear like this only in the form of language. Here sets are created. Here you have to think about the sets. A is related to B. If and only if B is divisible by A. B is divisible by A. For example, 6 is divisible by 3. 8 is divisible by 2. Or your 9 is divisible by 3. 12 is divisible by 4. 12 is divisible by 6. That is the meaning. B is divisible by A. Yani B is basically greater than or larger number. I mean greater than equal to. B is divisible by A and B both belongs to natural numbers. So let us see. Is it reflexive? Yani whether AA will come. Is a number divisible by itself? Is 5 divisible by 5? Yes. Is 2 divisible by 2? Yes. So it is reflexive because AA will be there. Is it symmetric? For example, 1 2 will be there because 2 is divisible by 1. But whether 2 1 will be there, is 1 divisible by 2? No. 1 2 will be there because 2 is divisible by 1, but 1 2 will not be there. I mean 2 1 will not be there because 1 is not divisible by 2. So AB is there, but BA will not be there because, for example, here, see here, 3 6. 3 6 will be there because 6 is divisible by 3. But 6 3. 6 3 will not be there because 3 is not divisible by 6. So it is not symmetric. What about transitive? If AB is there, that is B is divisible by A, and BC is there, that is C is divisible by B. So B is divisible by A, C is divisible by B. So obviously C will be divisible by A. Any AC will also be there. It means AC will also be there. For example, like this, you can think like this. 2 4. 4 is divisible by 2. 4 8. 8 is divisible by 4, which implies that 2 8 will also be there because 8 is also divisible by 2. So it is transitive. I hope it is clear to you. So it is reflexive, not symmetric, but it is transitive. So now let us move to this last question. Here the relationship is AB belongs to R. I mean your relation R is a subset of your relation R is the ordered pairs of AB such that 1 plus AB is greater than 0, where every AB, what is the meaning of this? For every, the meaning of this symbol is for every, and the meaning of this symbol is belongs to. Question is AB belongs to R such that 1 plus AB is greater than 0 for every AB belonging to R. This R means real numbers. This R means real numbers, and this R means relation. You have to understand, no? What is the language given? We have to understand. Here it is saying that R is a relation of AB such that 1 plus AB is greater than 0 for every AB belonging to R. This R is real number. So let us try to see here. Now we need to check whether AA will be there. For reflexive we have to check whether AA will be there. So if AA means 1 plus A square, is it greater than 0? Because AA means what? B is same as A. So 1 plus A square, and this is what? A square quantity, because A square plus 1. A square is always greater than 0 and A square plus 1 is a positive quantity. Positive quantity will always be greater than 0. It means it is reflexive. So this is true. I mean this is reflexive. What about symmetric? Symmetric means if AB is there, then BA should also be there. If AB is there, then BA should also be there. For example, like this. If 1 plus AB is greater than 0, then 1 plus BA is also greater than 0 only. Because AB is same as what? BA. If 1 plus AB, suppose A is 2 and B is 3. So 2 into 3 is 6. So 1 plus 6, 7. 7 is greater than 0. Then 1 plus 3 into 2, which is again 6, again 7. So that is also greater than 0. So that is what is the meaning here. Yani that is symmetric also. So your relation is symmetric also. Now we need to check about, so it is reflexive, it is symmetric. Now we need to check about transitive. So for transitive, I am going to take a simple case. Let us say that 1 minus 1 by 2. This is your AB. 1 minus 1 by 2. 1 minus 1 by 2. This is your AB. So what is the product? 1 into minus 1 by 2 is how much? Minus 1 by 2. And 1 plus 1 into minus 1 by 2. So 1 plus AB. This is minus 1 by 2. 1 minus 1 by 2 is 1 by 2, which is greater than 0. Yani this is included in that relation. Now let us check for, this is AB. Now let me create some BC. So the BC what I am creating is this. Minus 1 by 2, minus 1. This is my BC. This is my AB. This is satisfying this condition. Now this is my BC. So 1 plus the product of this, minus 1 by 2, minus 1, which is 1 by 2. And 1 plus 1 by 2 is 3 by 2. That is also greater than 0. It means AC should also be there. AB is there, BC is there. Then AC should also be there. So AC is what? 1 comma minus 1. Let us check. 1 plus 1 into minus 1. Minus 1. 1 minus 1 is 0, which is not greater than 0. So it is not transitive. Because AB is there, BC is there, but AC is not satisfying the condition. 1 minus 1 by 2 satisfies this. Minus 1 by 2 minus 1 satisfies this. But 1 minus 1 does not satisfy this, because 1 plus 1 into minus 1 becomes 0, which is not greater than 0. So it is not transitive. So it is reflexive, it is symmetric, but it is not transitive. This is the way you have to check. Even if one pair does not belongs to that, then entire it loses its generality. So these are the three problems. I mean, it is reflexive, not symmetric, not transitive. So if you see carefully, then this question, this, even in this question here also, and even in this, none of them are equivalence relations, because equivalence relation means a relation which is reflexive, symmetric as well as transitive. So none of them is a equivalence relation. So I hope these 4 questions are very much clear to you. Let me take another set of problems. You can note it down. Okay, so let us continue with these problems. So already we have solved 4 questions. So that would be question number 5, 6, 7, 8 and 9. Let us see what is given in these problems. Let us solve them one by one. Question 5 is, there is a set A containing natural numbers from 1 to 14, like is the 1, 2, 3 till 14. And your relation R is defined on set A such that is a collection of xy. How to read this relation? R is a collection of xy, ordered pair xy, such that 3x minus y is equals to 0, where x and y belongs to your set A. 3x minus y is equals to 0. From here can I write y is equals to 3x? Y is equals to 3x. 3x minus y is equals to 0. So y is what? Y is equals to 3x. So y, if y is basically a multiple of 3. Y is a multiple of 3. So here if you see carefully, then what will come in this your set A? I mean your relation R, you will have 1 comma 3, because 1 into 3 is 3. Then you will have 2 comma 6, because 2 into 3 is what? 6. Then you will have, the moment you go to 3, then what you will get? If you put your x as 3, 3 3s are 9. You will get 3 comma 9. Then if you put your x as 4, so 4 3s are 12. So you will also have your, 4 comma 12, because y is 3x. Try to understand, x y, ordered pair of x and y, but y is 3x. So if my x is 1, y will be 3. If my x is 2, y will be 6. If my x is 3, y will be 9. X is 4, y will be 12. X is 5, then y will become 15, but 15 is not there. So that is my relation R. Now this I have to check whether it is reflexive. So obviously it is not reflexive, because reflexive means 1, 1, 2, 2, 3, 3, 4, 4 till 14, 14. So this relation is not reflexive. Is it symmetric? 1, 3 is there, but where is 1, 3 is there, but where is 3, 1? 3, 1 is not there. So it is not symmetric also. Then what about transitive? 1, 3 is there, 3, 9 is there. 1, 3, 3, 9. Is it transitive? 1, 9. It is not transitive also. So that question is not transitive also. So I hope this question is clear to you. I mean 1, 3 is there, 2, 6 is there, 3, 9, 4, 12. This is your relation R. It is not reflexive because 1, 1, 2, 2 is not there. Symmetric 1, 3 is there. Where is 3, 1? Not there. Transitive 1, 3 is there. 3, 9 is there. But where is your 1, 9? So it is not transitive also. Let us go to the second question. AB, A is less than equals to B. AB belongs to R. So A is less than equals to B. This R here means real numbers. Real numbers, and this is your relation. So how to read the question? R is a relation. R is a relation of ordered pairs AB such that A is less than equals to B for every AB belonging to real number. So AA will come. Yes, AA will come. So it is reflexive. Why? Because A is equals to A. For example, 1, 1, 2, 2, 3, 3, 4, 4. That will be a part of this. Then what about symmetric? It will not be symmetric because 1, 2 will come. Because 1 is less than 2, but 1 will not come because 2 is not less than 1. I mean, you know the inequality in numbers. 1, 2 is there because 1 is less than 2, but 2 is not less than 1. So AB will be there, but BA will not be there. So it is not symmetric. What about transitive? AB, A is less than B. BC, B is less than C. If AB is there, BC is there, then it implies that AC will also be there, because if A is less than B and B is less than C, then obviously A will also be less than C. So it will be transitive. So it is not symmetric, but it is transitive. Let us go to the seventh question. This is your set A, 1, 2, 3. You need to find the smallest relation containing 1, 2 and 2, 3 which are reflexive and transitive, but they are not symmetric. Set A is there. We are forming a relation from set A to A. And we need to find the smallest relation. Smallest relation means it must contain the minimum number of ordered pairs. You need to find the smallest relation containing 1, 2 and 2, 3 which are reflexive and transitive, but that's not symmetric. So in my set A, 3 elements are there, 1, 2, 3. So my relation will become something like this: 1, 1, 2, 2, 3, 3. This is minimum because it is reflexive. Apart from that, 1, 2 and 2, 3 are there. 1, 2 is there, 2, 3 is there, because that it is given that that relation should contain these 2 elements at least. 1, 2, 2, 3. Now if you see carefully, it is reflexive because 1, 1 there, 2, 2, 3, 3 all are there. Now we need to make it transitive. So if you see carefully, 1, 2 is there, 2, 3 is there. 1, 2 is there, 2, 3 is there. But where is a 1, 3? So I am adding 1, 3. When I add 1, 3, it becomes transitive also. Now it is reflexive. 1, 2, 2, 3, 1, 3. So it is transitive, but it is not symmetric because 1, 2 is there, but 2, 1 is not there. So that is my relation R. So it is reflexive, transitive, but it is not symmetric. So this is that least or the smallest relation, which is reflexive, transitive, but not symmetric. I hope it is clear. Let us see question number 8. We need to have the set of all the triangles in a plane. T is the set of all the triangles in a plane. In a plane there are infinite triangles. That is your set T. So R is a relation of T1, T2, like this. Suppose this is your plane, and this triangle is there, this triangle is there, this triangle is there, this triangle is there. Like this, infinite triangles are there in this plane. They are saying R is a relation of T1, T2, ordered pairs T1, T2 such that T1 is similar to T2. I hope you understand the meaning of similar triangles. A triangle when it is said to be similar to another triangle. So for two triangles are said to be similar if you expand one of the triangles in proportion, or their sides are proportional to each other. That is, if you expand one of them, then it will fit exactly into another triangle. Or you may say their sides are proportional to each other. Sides angles are proportional actually. So that's all. It's not congruent. Congruent triangles are similar, but similar triangles need not be congruent. Congruent triangle means equal triangles. They will exactly fit into each other. But here they are talking about similar triangles. So first let us see whether T1 will come or not. Yes, it will come because every triangle is similar to itself. So it is reflexive. Now let us see whether symmetric. If T1, T2 is there, whether T2, T1 will come or not. If T1, T2 is there, then whether T2, T1 will come or not. If triangle T1 is similar to T2, then obviously triangle T2 will also be similar to T1. So it is symmetric also. What about transitive? So if T1, T2 is there, now here T1, T2 is there and T2, T3 is there. You know, condition of transitive. AB is there, BC is there, then AC should also be there. Now T1, T2 is similar. T1 is similar to T2, T2 is similar to T3. So obviously T1 will also be similar to T3. So it is transitive also. So this relation is reflexive, symmetric, transitive. It means what? It is a equivalence relation. It is a equivalence relation. I can say like that also. A relation which is reflexive, symmetric and transitive, then it is also an equivalence relation. I hope it is clear to you. Let us see this last problem. Set A is there. Set of all the, this is your JEE mains problem. Set A is a set of all the books in a library. In your school library, many books are there. That is your set A. Physics, chemistry, maths, biology, computer science, or your commerce textbooks, economics, your Hindi, Tamil, many textbooks are there. Relation R is defined such that is the collection of ordered pairs x, y such that x and y have same number of pages. Two books are there, x and y. Ordered pair of books x and y. X and y here are the books. What type of books? X and y have the same number of pages. Two books having same number of pages. Now let us see whether it is reflexive. So we need to have XX. Yes, because X and X are same books, so obviously they will have equal number of pages or same number of pages. So it is reflexive. What about symmetric? We have to check if XY is there, then whether YX is also there. If X and Y have same number of pages, then Y and X also will have same number of pages. So it is transitive also. What about, symmetric also. What about transitive? If X and Y are there and Y and Z are there, then we need to check whether X and Z are there or not. X and Y have same number of pages, Y and Z have same number of pages, so obviously X and Z will also have same number of pages. X and Y, two books are there having same number of pages, Y and Z are also having same number of pages. Let us say X and Y having 100 pages each, Y and Z also having 100 pages, so X and Z also have how many? 100 pages. So it is transitive also. It means this is reflexive, symmetric as well as transitive. It means what? It is equivalence relation. So that way you could have answered your JEE mains problem. So note it down, and I am going to take few more problems on this particular topic. This is a quite simple topic only as far as your mains and your board exams is concerned. Sorry, note it down. So let us continue with these questions. This is objective problem. Here it is given that set A is 1, 2, 3. We need to find the number of equivalence relations. Equivalence relation means a relation which is reflexive, symmetric as well as transitive. So we need to find the number of equivalence relations containing 1, 2. Yani this ordered pair has to be there, 1, 2. So let us do one thing. Total number of equivalence relations we have to find. So what we will do is first we will form the smallest equivalence relation, smallest, and in that we will keep on adding the ordered pairs and we will see how many more equivalence relations are there. So Let us create a relation. So equivalence relation means relation should have reflexive, symmetric as well as transitive conditions. So it means for reflexive 1 1 should be there, 2 2 and 3 3. This is must, so that it is reflexive. Now once it is reflexive, now we need to add 1 2 because it is said in the problem it has to contain 1 2. So we have added 1 2 also. Now it is reflexive, but it is not transitive because 1 2 is there but 2 1 is not there. So I am making it transitive, 2 1. Okay. So when I am making it transitive, I am writing 2 1. So now 1 2 is there, 2 1 is there, and for transitive 1 1, 1 1 is also there. And this relation is the smallest relation, which is equivalent relation, equivalence relation. Now what the ordered pairs we are left with? We are left with the ordered pair 1 3, 3 1, 2 3 and 3 2. If you see carefully, because here 1 1, 1 2, 1 3, 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. That many total number of ordered pairs would have been there, but this is the smallest equivalence relation. So one equivalence relation already we got. It means that 1 is there. Now let us see many more can be created or not. Now let us try to create one more. So what I am doing is I am adding 1 3. In this let me add 1 3. So let me say this is R1 R2. In this let me add 1 3. So 1 1 is there, 2 2 is there, 3 3 is there, 1 2 is there, 2 1 is there. Now I am adding 1 3. But if the moment I add 1 3, it loses its symmetricity. So I have to add what? 3 1. I have to add 3 1. Now if you see carefully, 1 3 is there, 3 1 is there. Why? So that it is symmetric. It is reflexive, it is symmetric. 1 2 is there, 2 1 is there, 1 3 is there, 3 1 is there. Now we need to check whether it is your transitive or not. So if you see carefully, here 3 1 is there, 3 1 is there, 1 2 is there, 3 1 is there, 1 2 is there, but where is 3 2? 3 2 is not there. So I have to add 3 2. But if I add 3 2, then I have to add 2 3 also, so that it is symmetric. Observe carefully, 1 1 2 2 3 3 1 2 2 1. This was already there. Now I am adding one more element. I added 1 3. But if I am adding 1 3, I have to add 3 1 also, so that it is symmetric. But if I am adding 3 1, what I am getting is 3 1 and 1 2. So I have to have 3 2 also. But the moment if I add 3 2, then I need to have 2 3 also. So with that, this nothing but becomes your universal relation. So my answer is 2. There are two equivalent relations. One is this one and one is this one. The second one is the universal relation also. So that is the answer. So number of equivalence relations are 2. I hope the question is clear to you. Now let us see this question. The question says that there is a relation R containing elements 1 1 2 2 3 3 on set A 1 2 3. So we have to choose the correct option. 1 1 2 2 3 3 on this. So obviously it is reflexive. It is symmetric also, because there is no 1 2. The condition is if 1 2 is there, then 2 1 has to be there, but there is no 1 2 here. So it is symmetric also, and there is no transitive condition also, because the condition of transitive is if AB and BC, then AC has to be there. But that if that condition is not there, see, if condition is there and if it is not followed, then it will lose the transitivity or symmetricity. But the condition itself is not there, so it is symmetric as well as transitive. So it is a reflexive also, symmetric also, transitive also. My answer is it is equivalence relation. I hope it is clear to you. This relation is reflexive, yes. It is symmetric also, because what is the condition of symmetric? If AB, then BA. Here if AB is not there, then why BA will be there? Similarly transitive also. So it is equivalent relation. Let us see this question. Why I am not going for this option? Because it is not reflexive only. It is reflexive but not only. It is actually all the three. The last question. Set A is the set of all the points in a plane, and there is a relation R. I mean, this is a set of all the points in a plane. Infinite points are there. Relation R is collection of your ordered pair PQ, it means is a collection of two points P and Q such that distance of point P from the origin is same as distance of point Q from the origin. So let us say this is your origin. So distance of point P from the origin is same as distance of point Q from the origin. You need to have the ordered pair, something like that. So let us do one thing. First let us check reflexive. So I need to check P comma P. P comma P. That is there because the distance of distance of P from O is same as distance of P from O because the points are same. So it is reflexive. Let us check symmetry. So symmetry means if PQ is there, then QP should also be there. If PQ is there, then QP should also be there, which is correct. If distance of P from O, and if OP is equals to OQ, then it means that OQ is also equals to OP. So it is symmetric also. Let us see transitive. So if PQ is there and QR is there, then PR should also be there. If OP is equals to OQ and OQ is equals to OR, then OP is also equals to OR. So that is also true. So that is the transitive. Basically, if you see carefully, this is your equivalence relation. This is your equivalence relation. And I hope you have understood that the collection of all these points is nothing but a circle. So that is, all these points are basically falling on a circle. The locus of all such points is a circle. So, and the distance was from the origin, is from the center of the circle they were talking about. So that's it about this part of relations. We'll meet in the next session with functions. Functions is a very important chapter for board exams, mains, and most importantly for your advanced. And you can continue with your school in text problems, and you can also go through your previous mains questions as far as this chapter relations is concerned. Keep on watching the videos, and many more things we are going to upload in physics and chemistry also. Download the app, all your mock tests, study materials, more videos, and many other courses are there on the application. So make full use of whatever we are providing. That's it as far as this session is concerned, and thank you. Keep on watching the videos. Thanks.